So good evening, everyone. So we'll start now. So from the next day from now, we'll always start at 6 p.m. Those who will join late can watch the video by rewinding it. All right. And how will we proceed is I'll give assignments or quizzes at the end of each class. Not each class. I'll try to give at every class after every class, and we will discuss those the solutions to those assignments first, and then we'll proceed to the planned part of the lecture. So we will start with the discussion of the quiz. Then we have to discuss search problems. So I have listed only 2 search problems because we discussed search problems in the last class. Then we'll discuss about search algorithms. Then we'll also see what are adversarial search when we have more than one participant in a search process, or you can take an example of a game where there are 2 agents competing amongst each other. And yeah, references. So this is the first question we had for the quiz. So it talks about mammals and lungs. So it says all mammals have lungs. Therefore, all things with lungs are mammals. So you see these kind of questions are actually logical questions. But if you think these questions as Venn diagrams, then it will be more easy for you to get to the answer. So I'll just show you, then we can discuss if there is some confusion. So all mammals have lungs. So you can think about that lungs are a bigger subset. Just so this is lungs, and all mammals have lungs, and mammals are a small subset, right? So all mammals, so all the set of mammals are inside the set lungs. Therefore, all things with lungs are mammals. So that is not true, obviously, because lungs is a larger subset than mammals. It may happen that all lungs are mammals, but it is not always, it may not be always true. Therefore, this is an invalid argument. All right. Any doubt?
No.
Okay, so all unicorns are magical. So which is the larger subset here? If we think about this problem as Venn diagrams again. Which is the larger set, so unicorn or mammal? Magical.
Magical.
The magical.
So this is magical, and unicorns will be a smaller, right? And all magical things are rare. So you see, there can be multiple sets which are rare. You can have this set which is rare. You can have this set which is rare, right? So this set rare has some. So sorry, all magical things are rare, right? Just a minute, I have not drawn it correctly. All magical things are rare. So magical things are inside the set rare. Now, therefore, all unicorns are rare. Obviously, when the unicorn are inside the set magical and magical is inside the set rare, then all unicorn are inside the set rare. Therefore, this is a valid argument. I have given another explanation. You can go through the explanation. It's just different way of coming to the same conclusion. All cats are independent. So which will be the larger subset?
The independent.
Independent, right? So independent will be the larger subset, and all cats are independent. So all the set of all cats will be inside independent. No independent animal are no dependent animal are independent. So this is obvious if you think about this in terms of sets. All right. So if this set represents independent, so this outside region will give you not independence, right? The set of not independent things. Therefore, no dependent things are cats. So this is also obvious because cats is inside independent and no independent things are dependent. Therefore, no dependent animals are cats. So this is a valid argument. And over here, we have assumed that this independent and dependent, the union of these 2 sets forms the universal set. It might not be true because these are just some phrases. You cannot take it as literal English. All right. So we have assumed here, not for the solution of this problem, for this Venn diagram, we are assuming that independent and dependent are so union of that, both of them are the universal set, and both are disjoint. And even if you don't solve using the Venn diagram, you will come to the same conclusion that this argument is valid. All artists are creative. Again, creative will be the larger subset and artist will be inside it. All experienced people are studied. You see, again, sorry, this is creative. So all experienced people are studied. So I have a set studied and experienced people inside it. Now you don't know what is the intersection between these two sets. These are talking about very two completely different sets. So you'll not be able to come up to any conclusion. Therefore, this argument is invalid, right? Both sets, we have no idea of the overlap between these two sets. So we cannot come to a conclusion. Then therefore, this argument is invalid. Any questions in this? All right. So no fluffy creatures are purple. So there's a purple set. This represents purple. Sorry, purple. No fluffy creatures are purple. So I have a fluffy creature, which is a set FCIL, right? And I have a set purple. All purple things are from the moon. So I have a set moon, which is a larger set, right? All purple things are from the moon. Therefore, no fluffy creatures are from the moon. Now you see, no fluffy creatures are purple. So there is no intersection between purple and fluffy creatures, and all purple things are from the moon, right? So no fluffy creatures are from the moon.
Shubham, just a
Yes.
question over here. We are saying all purple things are from the moon, right? But
Yes.
there is no point that fluffy creatures can't be from the moon.
Yes. Yes.
There is not
Yes.
mentioned over there. So there could
It
be a
can be
uh,
like well.
yeah. So this could be a bigger picture.
Yes. 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 True. This is true. You're true. So the question is, no fluffy creatures are from the moon. Okay. So have I done something wrong in this question? Can help me, by the way. So these are logical questions. I can also get confused. So I'm asking, no fluffy creatures are purple. So no fluffy creatures are purple. This is for all purple things are from the moon. So all purple things are from the moon. So no fluffy creatures are from the moon. I have no fluffy creatures. So actually, I guess this will be an invalid. I'll check this. I guess from this discussion, I feel that this is an invalid argument. I
Yeah,
will
I
check.
feel the same. Yeah.
I'll check this again and I'll let you know. All right.
Yeah, sure.
Any doubt? All right. So question number 6. So no cars are bicycles. So I have a set car and I have a set bicycles, and there is no intersection between the two sets. No bicycles are fast. So I have another set. So it can be like this, or it can be like this, or it can be like this. All right. So we can have multiple. No bicycles are fast. So either this can be fast set, either this can be a fast set, or this can be a fast set. Therefore, no fast things are car. So this is not true, right? There can be multiple sets and you cannot come to a conclusion that no fast things are car, because if this is the fast thing, then you see there is some intersection between car and fast. So this is an invalid argument. All right. Now over here, a person is saying, I always lie. Now you have to think about cases. This person can be a truth teller or he can be a liar. All right. So if he is a truth teller, he will always speak the truth. And this statement, I always lie, will contradict that he is a truth teller. Because if he says I am a liar, but he is actually a truth teller. So this is a contradiction. So he cannot be a truth teller. Now suppose if he is a liar. So we are what are we doing? We are using contradiction. All right. So we are proving things with contradiction. Now I'm saying that he is a liar. So if he is a liar and he says I always lie, then he's actually telling the truth. Therefore, he is not a liar. So we are coming to a contradiction. First, we are saying, let us assume he is a liar and he is making this statement, and this statement is a truth. A liar cannot tell the truth. Therefore, he is not a liar. And we are contradicting our first assumption that he is a liar, and therefore this is also not true. Therefore, he is making a self-contradicting statement. All right. So this neither a liar nor a truth teller can tell this statement. They cannot say this statement. All right. Any doubt? All right. So a person says, if it rains tomorrow, I will stay indoors. All right. So this is an implication. If this happens, then I'll do this. Now, you cannot say if he's telling the truth or lying, because this can be a truth statement or it can be a false statement as well. But you can say that this is a logically valid statement, right? There is nothing flawed with this statement. So this is just an implication. If A, then B. So we write implication like this: A implies B. It means if A happens, then B will happen. So it says that if it rains, I'll stay indoors. So this is a logically valid statement. All right. So this question, so there was error on my side with this question. So what was the error? I forgot to mention this assumption. All right. So this assumption is very crucial for the solution to be unique. If this statement is not there, then the solution will not be unique. I'll explain the question once again. There are 3 people and they are wearing hats. They can see the other person's hat, but they cannot see their own hat, right? And they are saying that, so if they see at least one hat, then they have to raise their hand. All right. So if I am a person in this among the 3 people, and if I see a red hat, I'll raise my hand. What was the critical thing I did not write? The critical thing is I'm not able to conclude what is the color of my hat. All right. So if I see there is one red hat or one blue hat or some configuration I see, and I see that we are raising hands because we know that all 3 are raising their hands. I'll not be certain about the color of my hat. That is one assumption, very valid assumption. All right, not valid, crucial assumption. So what? So we'll reason it out. All right. So suppose all the 3 are wearing. So I'll just I'll not go through this. All right. I'll just use a page and then explain. So suppose there are 3 person A, B, and C. So there can be 4 cases actually. The first case is all blue. The second is 1 red and 2 blue. The third is 1, or I'll write 2 red and 1 blue. And the fourth is all red. Right. So first, if there are all blue, then I am seeing 2 blue hats. The other person is also seeing 2 blue hats, and the next person is also seeing 2 blue hats. None of them will raise their hand. So this cannot happen. All right. Now for this second case, when one is wearing a red hat, so suppose A is wearing a red hat, B is wearing a blue hat, and C is wearing a blue hat. If we talk about the person A will see 2 blue hats. Therefore, he will not raise hand. And this is not what we see. We see that all 3 raises their hand. Therefore, this is also not correct. This case cannot happen. We'll talk about 3, but first let us talk about 4. We will come to 3. Suppose all 3 are wearing red hats. So if I see, so all 3 are wearing red hats. So I can see that both of them are wearing red hat. If I see at least one red, I'll raise their hand. So all 3 will raise their hand. So this can be one potential solution to this question, right? So one potential solution. Now coming to the third case where there are 2 red hats and 1 blue hat. So let us assume that A is wearing a red hat, B is wearing a red hat, and C is wearing a blue hat. All right. So we will go into the so we'll suppose we are player C. So if I am player C, I will see 2 red hats. I will raise my hand. Right. Okay. If I am player B, I will see 1 red hat. I will raise my hand. If I am player A, I will see 1 red hat. I'll raise my hand. So it seems that this can also be a solution to this problem. But we have an assumption. What is that assumption? That none of the players can be certain about their own hat. That will have a clue that this cannot be a solution. So we will just reason it out. All right. Now we will see. Suppose I am player C. What I see is A is also raising their hand and B is also raising their hand, right? So A is also raising their hand and B is also raising their hand. So what C will think? So we will think about what C is thinking. So we are in C's perspective now. All right. So we are in C's perspective. What will he think? He or she will think he will think that B is raising his hand, his or her hand. B raises hand. Raise hand. All right. Now, since B is raising their hand, B is seeing one red hat in A, and A is also raising a hand. A is also seeing the red hat in B. All right. So we have thought about C. Now suppose we are B. So we will now reason out if I am person B. Now if I am person B, I am seeing one red hat on A and one blue hat on C. Now I am B. I see that A raised their hand. What A does? A is raising their hand. If I am B and A raises their hand, and I can see that A has a red hat. If I have a blue hat, then A will see two blue hats, right? So what A is doing? A is raising his or her hand. So A is raising his hand. So A must see one red hat. What is B thinking? B is thinking कि A ने हाथ उठाया है. A has raised his hand. He is the one wearing a red hat. So therefore there must be one more red hat in front of him, right? B will think कि A ने हाथ उठाया है. Since A has raised his hand, he must have seen one red hat. That red hat will not be on C's hat because I can see the B can see that C is wearing a blue hat. Therefore, B must be wearing a red hat, right? Think about in B's perspective. I'll repeat again. Everything I'll repeat again. What B sees that there is one red hat and one blue hat. Red hat is on A's head. Now he will think what A is thinking. A is thinking because he has raised his hand, he has seen at least one red hat. It is not on C because I can see C's hat is blue. Therefore, that red hat must be mine. That is why A is raising his hand. Therefore, B can conclude that my hat is red. And that contradicts with the assumption that no one is able to deduce his own hat color. Therefore, this will not be the solution to this problem, and only solution is all are wearing red hat. Is this clear?
Yeah, everyone. Got it.
Anyone, any doubt? Okay.
Shubham,
Yes.
I'm Saurav.
Yes.
I had actually query during, when the answers
Yes.
were out.
Yes.
So my point again here is that, see, if we are looking after all red, that all now we are coming out to the solution with respect to perspective of everyone.
Yes.
However, my point is that, see, in the there's a option that at least one of them is wearing red.
At
At
least
least one is wearing a red. Yes.
red hat. Yes.
So this is particularly with respect to the options available. This is the most likely solution.
Acha, what does it mean at least one is wearing a red hat? It means all these three cases, right? All these three cases. One red hat,
Correct.
and three red hat. But we have
Correct.
reasoned out that two
But
cannot be.
again, Shubham, my point here is that it is, with respect to all wearing red hat, that cannot be ascertained.
Why?
Even if two
Is that
people are wearing red and one is wearing a blue hat, then
Hmm.
also all will raise the hands.
Yes, if two people are wearing red
So
hat and one is
yes,
wearing a blue hat, all will raise their hand. But this
correct.
assumption,
And even all yes.
this assumption will not make that option correct. Sorry, not this assumption. This
But that
assumption
is given in the question.
that was not in their question, right? So if that was not in their question, then 3 and 4 would be correct. 3 and 4 would be correct. So the correct solution would be.
Shubham. Hello. Shubham,
Just
this is Jay.
just let
Let's
me
take one example. You are wearing blue hat. With you, Saurav and I are standing together. You are wearing blue hat. We both are wearing red hat. Now,
Yes.
how many hands will be raised? You don't know what kind of hat you are wearing. You will raise your hand because you are seeing red hat. Saurabh will raise hand because he is seeing my red hat. I'll raise hand because Saurabh is wearing a red hat despite knowing each other's hat color. So in this
Correct.
case, two red hats are worn and one blue hat is worn. And
Yes.
three is by default true because all three are wearing red hat. All the hands will be raised. But in this case, Saurabh and I are wearing red hats and you are wearing blue hat, but still all the three hands are raised.
Right. Right.
So
In
this is
second case,
also, I'm still considering the assumption that you are not knowing the color of your hat.
no. In such case,
No.
one.
You are not. Just now we saw that you don't know the color of your hat, and still all the three hands were raised.
Acha, let me explain now. Okay? Let me explain. So if there are two red hats and one blue hat, the two people who are wearing red hat can deduce कि मेरा hat red है. मतलब अगर इस केस में, for this example, if A is wearing red hat and B is wearing red hat and C is wearing blue hat, A and B will know for sure कि उसका hat red है.
Why?
हाँ, I will explain again. No problem. But just listen carefully. Think about B's perspective. B sees कि सबने
Here actually, I think it is like this, that it is not that nobody can see their hat. It is nobody can conclude their hat. This is the difference. If nobody can see their red hat, then two red, one blue is maybe correct. But here nobody can conclude their color, because of which all three are correct. That nobody can see their red hat and nobody can conclude their color of hat is different. That logical, these two sentences are different, because of which all red hat is the correct answer. Am I correct?
Yes, sir. Just let me explain. I guess there might be some doubt. I will explain again. So you see, the point of this question is, one big assumption is there that the person, no person can able to deduce कि उसका hat का color क्या है. So for example, in this case, if A is wearing a red hat and B is wearing a red hat, so you see, suppose we are placing ourselves in place of B. B sees that all are raising their hand, right? He sees that A also raises his hand. If A raises his hand, he must have seen one red hat because he is raising his hand. And I see A is wearing a red hat and B is wearing a blue hat. Therefore, the only hat A can see, which is red, is mine, right? Therefore, B can conclude कि मेरा hat red है. That's why A is raising his hand, because the red hat he is seeing is on my head.
That is correct, but according to question, if no one can deduce their own, yes.
So if this assumption was not there, suppose that assumption was not there, then the correct.
Correct. Then correct.
At least one, at least two are wearing a red hat. That would have been a correct answer. Not one, two. Right?
So then probably all are wearing red would be the correct answer in that case.
And also two red hat and one blue hat. Both of them will be the correct answer.
Correct,
Therefore, the
correct
will be at least two are wearing a red hat. That would be the correct.
Correct. At least two are, yeah.
Not one, two, right?
But yes, correct. Yes. But now, if in the question it was mentioned that no one can deduce the color of their own hat with certainty,
Yes.
again with certainty, then since we cannot ascertain with the proper, all wearing red hat cannot be possible in all the cases. Again, if one is wearing blue, again everyone will be raising their hand. So that is why I think at least one is wearing a red hat is the answer.
Okay, Saurabh, what we can do is after the class we can discuss for
correct.
We will discuss this. All right. So yeah, so I have just written it out again here. So what we did last class is we discussed about search problems. Now before going to today's lecture, first let me let you know few things. You see what we are doing over in this search problems, which we'll see in this week, is constructive heuristic. We label this as constructive heuristic. what does constructive heuristic do? It constructs a solution. So one by one piece at a time, it will bring and it will tell me what is the solution. So for example, a very famous problem in operations research and computer science is a traveling salesman problem. TSP. What is a traveling salesman problem? So it is not related to today's lecture, but this is important to let you know about these things. So what is a traveling salesman problem? So suppose there is a salesman who wants to visit n cities. So there are n cities, 1, 2, and so on till n, and he wants to visit each city exactly once, and he wants to come back to his home city, suppose n. So what constructive heuristic will do is it will build a solution. So suppose he's starting from 1, then visits 3, then visits 5, then visits 4, then visits 2, and then visits 1. So suppose there are 5 cities. So this is what a constructive heuristic will do. It will build the solution one piece at a time, right? So it started with 1, then it says, let us see, I hope 3 is the next city he will visit. So he will put 3, then it will put 5, then 4, then 2, then 1. Then we have got a solution. This is how a constructive heuristic works. It builds a complete solution. What is a solution? A permutation of cities. So if you remove 1 from over here, because we know that he is starting at 1 and he will come back to 1, then it starts from 1, then 3, then 5, then 4, then 2, and then back to 1. So this is one solution to this problem, right? This is a complete solution. Constructive heuristic will build this solution one piece at a time. There is another kind of technique of solution methods which takes one solution and tries to come to another solution, a better solution. Those kind of search are somewhat related to local search if you're talking about heuristics, right? So what it will do is it will start with a solution. So suppose it is starting with 1, 3, 5, and 2. So this is one solution. It is a complete solution. So it starts with a complete solution and it says that let us go to another solution which might be better. So suppose 1, 4, 3, 5, 2 is another solution. So it will go from this solution to the next solution and from this solution to the next solution. So this is another kind of search which we're not talking about today. We are only talking about a search which construct a solution. So for example, if we're talking about in our last class that what is the path the farmer will take to cross all the 3 objects he have, persons or whatever it is, 3 objects he has. So we are constructing. So first what we'll do is the farmer will take the cabbage, then he will come back. So we are constructing the solution from scratch. We are not starting key, this will be one solution. Let us see if there is a better solution or the other or not, right? We are talking about constructive heuristic. Yes. Okay. So I guess someone is unmute. Please unmute yourself if you don't have anything to talk about. Okay. So so what we will do is I have 2 problems. You can try and formulate it as a search problem. So what do I mean by formulate it? Write the states, then the actions, then the transition state, and so on and so forth. All right. So I have taken this problem. So this problem is inspired by some lectures. You can go. I have referenced it, everything in my slide. So what is this problem? So you see, suppose there is a warehouse at location 0. And I have locations numbered 0 to n. So it is numbered locations 0, 1, 2, 3, 4 till n. And there is a manager and he has to send a good from warehouse 0 to warehouse n. Now he can use 2 kinds of trucks. So a standard truck, it costs ₹1. And what that truck do is if it starts with X, so because we have labeled the cities from 0 to n, and I'm saying if the if the truck starts with city X, it will take that good to X plus 1. All right. So if it starts with warehouse X, it will go to X plus 1 and it will cost ₹1. There is an express truck with cost ₹2 and it moves the good from warehouse X to warehouse 2X. So if we are at city 10, this express truck will take it to 20, right? And the cost will be 2. The question is, what is the correct? So what is the minimum cost transportation he should take when starting from warehouse 0 and he wants to send that good to warehouse n? All right. So this is the question. All right. So I'll just show you. So suppose this is 0 and this is n. There can be multiple paths like this, right? but he has to end at n. He cannot overshoot n, right? He cannot overshoot n. He cannot overshoot n. So this is what he has to do, and the cost should be minimized. So this is a problem. You try, you think about what can be a state of this problem, what can be the, so I'll show you the various components. So I have just labeled it. So I'll tell you the various components. Just let me go to the slides here and reason out the various components. So the components of a search problems are state. What can be a state of this problem? The initial state, the actions you can take at any state, the transition model. So if you are at a state and you take this action, you will, what state you will be. So that is known as the transition model. The state space, what will be the complete tree look like, the goal test, and the path cost. All right. So let me see. I can just go back and use so show you the lecture 1 slides maybe. So this is lecture 2. I'll go back and show you the lecture 1 slides, and over here I have the states. Yes, so these are the various components of a search problem. Okay, I'm sorry. The state, the initial state, the actions, the transition model, the state space, the goal test, and the path cost.
Kindly share the problem statement again.
Yes. You see, modeling is a very important skill if you want to develop algorithms. Before solution approach, you should know how to model a problem. So this is one assignment kind of thing you are doing right now, modeling a problem.
Shivam, please share this slide of different stages.
Yes. The
Hold a second.
Sorry.
Okay, thank you. Okay.
All right. So we don't have a lot of time, so I'll just tell you the answer. You can just match if you got it or not. All right. So you see, these numbers can be thought of as the state of a problem. So because you see, at any state, if you take this as the number, you can tell me if you take an action. So there are actions in this. You can think about this delivery trucks as action. So there can be a standard truck action or a express truck action. And if you're at any warehouse, suppose you're as warehouse X, and if you assume that as the state of that problem, and you take an action, suppose standard truck, you will go to a X plus 1 state. So the state of the problem is just X, the warehouse you are at. The initial state is 0. The action is either standard or express. The transition model is, if you give me a state and an action, I'll give you what state you will be. All right. So if you are at X and you are taking action express, you will be at 2X. The state space will be all possible actions you can take while starting from 0 to reach. Over here it can be n. Yeah, if you have to reach n. So all possible actions you can take. You can just reason out how many possible. So what will be the tree? It will be a huge tree, right? You can just take 1 1 1 1 1, or you can just take 1 2 1 2 1 2, or there are many multiple such branches will be there in the tree. What is the goal test? You can just check if the state is just equals to n or not. And path cost will be when you have completed when you have reached the goal, you will just come back and trace the total cost you incurred to reach that goal n, right? So this is the modeling. I have one more problem, and after that we'll see the algorithms to solve search problems. So this is a maze problem, but think about practical applications of maze. So a robotic arm, it is here and it wants to go to another location, and there are objects kept in its path. So what path that robotic arm should take such that it grabs an object and keep it in another object, and there can be multiple applications of a maze. All right, so this is one maze problem. Take a minute, read the problem, and think about the modeling aspect of this problem. And this example is inspired by this lecture series. What can be a state of this problem?
all
So you can think about a state as the path you have. Yes, yes.
It can be any of the white boxes.
Not exactly. You will not know. So if you are saying that this is one state, right? So any of the white boxes. So you'll not know how you have reached over here, right? So for example, if you go back to the problem of that farmer, and if I say you are at a how will I put it? So suppose you are saying that this is a state, right? And you can tell me that you are taking up. So if you are here and you are taking an action, suppose down, so you can tell me you can come to this state, but from where you have started, the path you have taken will be a better way to put a state, because when you come back, trace back, you will not be able to trace the whole path, right? So if you have reached the goal state, you will not be able to tell me the complete path you have taken. So yeah, so I'll just show you. So I have written here the path can be x and y, but along with that you have to take the parent. So suppose you are at x and y, you should know what is your parent. Otherwise you will not be able to go back, right? So this is the state. The initial state is 1, 5. Along with that you should know that your parent is none. So along with that you should know your parent is none, right? The action can be up, down, left or right, but there are walls. So some actions you will not be able to take at some of the states. The transition model will take a state and an action and give you the next state you will be. All right. And remember, I'm telling you that the state should have a parent, otherwise you will not be able to trace back. State uh, all possible x comma y and its parents will be the state space. The goal test is just you have where you are right now. If it is actually equal to the uh, cell you want to reach, will be the goal test, and the path cost is here nil. You can take any path, but you can think of this as a path cost. You can say that I want to reach the goal with the shortest path. So there can be a path cost of unit length. So the step you are taking is a unit length, and you can say this unit length cost I want to, so it will sum up. When you reach the goal, you want to minimize that path cost. So there can be a path cost. So each step you take in the maze cost 1, and the summation of all the cost can become your path cost. All right. So there can be a path cost. You want to reach the goal with the shortest cost, or shortest path you want to reach there. All right. So this is another modeling. Now we'll talk about the search algorithms to solve these problems. All right. So this is backtracking search. Before that, do you recognize this tree? This is same as what search space search that modeling is. You are at any stage, you can transition to any other state. So this is how you can represent that model using a tree, right? So what is backtracking search? Backtracking search is a very naive algorithm. What it does is it goes to the end of the tree. So it starts with here and it just goes as down as possible, and at every state it checks if it is the goal state or not, right? And then if it has reached a goal state, it will take the cost of that state, right? So suppose A is the goal state. Now the algorithm will tell me that I have reached a goal state A, and it will compute the cost. So suppose the cost is 100. And what is the objective? My objective is to minimize the cost of reaching this state A. But I don't know if there is some other path or not which can take me to A with a cost of less than 100. So what this algorithm will do, it will explore the whole tree. So it will go down, it will see that this is not A, then it will come here, it will come here, it will come here, it will see this is not A, then it will go back and then come here, it this is also not A. Now it will go back and come here, it will see it is not A, come here, it will see it is not A, come here, it is not A. Actually it will search the whole tree. And why it is known as backtracking search? So whenever it has reached a leaf node. So what is a leaf node? I'll tell you what is a leaf node for now. Just let us assume C is the leaf node. So when it has come to a leaf node, it cannot go down. So it has to backtrack its path. So it will go to A again and then go to D. So that is why it is known as backtracking search. But it's just exploration of the whole tree. It is not a very good algorithm. If your search tree is very large, it is very difficult to converge to a solution. All right. Now, what is a leaf node? In a tree, there is a root node where the branching starts. So over here, S is the root node. These are not very important, but I am telling you because I have come over here. So this is the root node, and a leaf node is where there is no other child. So whenever a node branch, we say that these two are the child of S. So A and B are children of S. And a leaf node is where it doesn't have a child. So M here is a leaf node, N is a leaf node, C is a leaf node, and so on and so forth. All right. Now, why are we exploring the whole tree? We are exploring the whole tree because there can be another path of a cost which is lower than the cost which I have encountered till now, right? So suppose this A node and E node both are the solution to this problem. All right. So suppose in this maze problem, this can be one path, this can be another path, right? So there are two paths. So in this tree, suppose those paths are represented as A and E, and I don't know if A is lesser cost or E is lesser cost. And I also don't know if there are other paths as well. So suppose L is also a solution to this problem. Unless and until I explore the whole tree, I will not be able to tell that this is the optimal solution or not, right? So that is why we are exploring the whole tree. Now the advantage of this algorithm is that the path cost can be anything. So the action cost, so the cost you are taking for each action can be anything. It can be a zero, it can be negative, it can be as large as possible. This algorithm will guarantee that you have found an optimal solution, whatever be the past cost. It can be negative, it can be zero, it can be as large as possible, as large positive number as possible, right? Now this space and time, I'll let you know what is this, but if you have not taken any algorithms course, then you will not be able to understand this very nicely, because this O something, if I write inside it, yes.
So what do you mean by action cost can be negative?
So suppose there is a path where you have a negative cost. That is what it means. I cannot tell you one real example right now because I don't remember, but there can be some path where the cost is negative. I don't have any right now. I don't have any example, so I'll just think about some example in the next class or tell you. But there can be a tree where, or a graph with negative cost edge.
For an algorithm, there can be negative cost, no cost, or a positive cost.
Yes.
Is it like that?
No. I'm sorry if I have not been able to make you understand. So I'm saying that, you see, if I take this path, there will be a cost. So for the maze problem, the cost is 1. If I take this path, the cost is 1, right? I'm taking one step. So it means for each action, what is the cost? Action cost.
1.
Right? Now what I was saying is this O, this is actually the worst case analysis. And if you have not taken any algorithm course, it will be difficult for you to understand. Nevertheless, it is, you might or might not need this in your future. So don't worry about it a lot. So you see this algorithm, whenever it is down here, what is the memory it has to keep? The memory is what path it has taken to reach C, right? So when C is not a solution, it just forgets that we have taken this path. It takes this and it remembers that we have come like this and like this. Then like this, it will remember only the path it takes to reach that node, right? And I label this the depth of the tree. So this at one level. So from one parent to a child, I'm saying the depth is 1. So this is one depth. Again, this is one depth, and this is one depth, and this is one depth. So the total depth of this tree is 4, right? There are 4 stages to this tree. There are 4 levels. So level is the technical term. Over here, I'm saying that is D. So the memory it has to keep is actually order D. It says in the worst case, it has to keep memory in. So when you are doing an algorithm, you have to keep the memory of the path you took to reach to that node. So in the worst case, you will at max keep D, so order D. So that is how it means. All right. And time, what does time say? You see, this small b is the branching factor. So over here we have b is equals to 2. So at each node, I have 2 branches. So over here b is 2 and d is 4. D is the depth of the tree, the levels it has. So it has 1 level, 2 level, 3 level, and actually 4 level, right? So how much time it is taking? You see, at any node, it has 2 branches. And at each level, there can be at max 2 branches. So right, so suppose it is here, it can have 2 branches. Over here it has 2 branches. Over here it has 2 branches. So at a level, it has 2 branches. The next level it has 2 branches. So it will be b to the power d in the worst case. In the worst case, right? So suppose you are thinking that the tree is complete. So it is not ending over here. It is complete tree. So in the worst case, it will take b to the power d amount of time, right? So if you're not able to understand. Yes.
So in this particular case, in both the branches, you are taking number of branches to be 2. What if the one node is having 2 branches and the other branch is having 3 branches?
So you have to take the maximum branching factor. The branching factor is actually the maximum.
So 3 raised power d, whatever the depth is.
Yes. Oh. So in worst case, it means कि सबसे बुरा क्या हो सकता है? So सबसे बुरा it is b to the power d, and whereas b is the maximum number of branching you have at any node, and d is the maximum depth you have to take. So at the worst case, this is the time you will take b to the power d of that order, right? So this is known as the worst case analysis. Complexity analysis पे पढ़ता है. It's actually helps to tell you how good is an algorithm, right? So this was backtracking search. Any questions over here? All right. Depth first search. So you see, whatever algorithms we'll discuss today, it will be very slight improvement of backtracking search. We will not have a lot of improvement. And these algorithms like depth first search, and we will also see breadth first search, these are special use cases of backtracking algorithms because it is very minor. It is doing very minor changes. What is depth first search? It will go to the depth first. All right. So it will go to the depth over here. If it will see that C is not a solution, then it will come back and then go over here, then go over here, and then go over it. So it is just like backtracking search. It is doing backtracking search. All right. Now you will ask me, how is this different than backtracking search? So depth first search assumes that the action cost is 0. So when you are going from S to A, the cost is 0, A to C, the cost is 0, A to D, the cost is 0, and so on and so forth. So all the edges have a cost of 0. How will this help? So suppose M is the goal. This is the goal you want to reach. Now, if M is the goal and you have reached the goal, the path cost, the complete cost will be 0, you know. And any other solution will have a cost of 0. So if you have obtained a goal, you don't need to search the whole tree. You are at a goal. That's it. So this is how depth first search reduces some, so it will, in the worst case, it will take the same amount of time. So suppose L is the solution. If L is the solution, and if you're starting like how we have done today, done now, so it will go here, then come here, come here. In the last case, it will reach L. So in worst case, it is same as the backtracking search. But on average, we see that depth first search performs better than backtracking search. I'll repeat again. We assume that the edge cost, action cost is 0. So whenever I reach a solution, I say this is the solution, because we don't bother about the cost of reaching to that node. In such cases, depth first search works. Is it understood?
Yes.
Yes.
Any doubt? Yes.
One more doubt. One of the differences between backtracking algorithm and depth first search is, upon reaching the goal, depth first search stops, unlike backtracking. Is it true?
Yes.
Okay.
Yes. Backtracking search will not be able to tell you if this is the best solution or not. But in depth first search, every solution is the best solution because all solution will have a cost of 0. And therefore you don't need to search further. You just stop.
Okay.
Right? So the space complexity will be same as backtracking search, and time complexity will also be same because these are worst case complexity. In the worst case, it will take same amount of time, right?
But
so
in case of
yes.
depth search, this depth first search algorithm, in this case, all costs are 0.
Yes, sir.
So all costs are 0 means all optimal solutions are 0. I agree.
Yes, sir. All solutions are optimal solutions.
All solutions are optimal.
Yes, sir.
Wherever the then values will be given for this path, then this search algorithm is not suitable, because this is a special case when we are considering the path costs are 0.
Yes, sir.
So
yes.
wherever path cost will not be 0, then there we cannot apply this depth first search algorithm.
No, sir.
Okay.
Sir, if you are coming from that OR background, and if you are thinking about in branch and bound algorithm, we use depth first search and breadth first search. So if you are coming from that area, then you will realize that in branch and bound algorithm, we use more concepts than this. We use node pruning. So there is lower bound and upper bound, and we prune nodes. So those are the things we are not talking about here, right?
Okay. Thank you.
Now, so why I have labeled this tree over here is because I wanted to show you how depth first search keeps memory, right? So how it keeps memory. So depth first search actually uses a stack. So I have kept one more example, by the way, later. All right. So what is stack is actually last in first out. So think about it as a stack of books. So whatever book you will keep at the top, that will be removed. So why I'm talking about this is when you code this algorithm, you would need this idea. How do you know in code that you have to reach this node first? You will not be able to know in code, right? Because you cannot visualize the tree. It can be any tree, any length, any breadth, right? So it uses stack. I have taken one example in later slides. We can go there and then see and come back here if needed. All right. So just for idea, I wanted to tell you it uses stack. And when we go to breadth first search, over there it uses cube. These are data structures. If you have taken a course on data structure, you will be able to understand. And if you have not taken, it's not very important right now. It's important, but the idea of all data structures are not important. So what is the stack? So stack is just a pile of, suppose you can take it as a pile of books. Whatever you put first, you have to take it out first. So whatever you put last, you have to take it out first. So last in, first out. So for example, over here, if you are at node A, So you can put, so if this is the stack, if you put A first, because you're starting at A. So you have put A, what is that you are, what is at the last? A is at the last, you take it out. I'll just erase A for now, right? Now, when I have explored A, there are two children, B and C. You can put them in any order. So suppose I have put B and then I have put C, right? Now, what is at the last? C is at the last. So I'll take C out. So what I'll do, I'll take C out. So I've taken C out. I'll put the children in any order. It doesn't matter. So I'll put F and G, right? Now what is at the last? G is at the last. So I'll take out G. I'll take out G. So I have explored A, I have explored C, I have explored G. Now when I have explored G, its children is J. So I'll put J over here and I'll take the last one out. So I'll take out J. So I'll take out J. Now when I take out J, its children is K. So I'll put K in the stack. So this is what is a stack. Now the last is actually K. So I'll just take out K. What is its children? M and L. So I'll just light M and L, right? Now I'll take out M. So when I take out M, you see, when I take out M, you see we have reached this path. So this is actually, you see, depth first search. You're going in the depth first and then you're worrying about other branches. So when you have take out M and you see there are no other children, then you go back to your stack and take out L. So when you take out L, this will be your stack. You explore L, then you explore L, then you backtrack. So you go and you see we have F in the stack. So you take out F. So when you take out F, you will, you will put in the stack its children. What is its children? I. So you'll put I over here. Now you have explored this. So you'll take out I. Sorry for this back and forth, but I cannot help. Now you go back and you see in the stack you have only one, which is B. So you are coming over here. So you're taking out B. When you take out B, you will add its children. What is its children? So it is D and E. You can add its children in any order. It doesn't matter. You will take out E. You will explore E, and then you will explore D. So you see you have just done the same thing, but using a data structure. So this data structure helps you to do the depth first search. All right. So this is how a stack works. Any questions?
No questions.
All right. So if you know Python, you can just take a list and just put it always at the end and take out always from the back. So that is how a stack, you can build a small stack. All right. Just take a list, always add at the end and always pop from the end. OK, so this is the maze we were talking about, and we will see how depth first search works over here. You can just do the same using the stack, but I'm not doing it because it will be cumbersome. Every time I have to put in and then take it out, put in and take it out. You saw that for this small tree, we had to do so many iterations. So that is why I'm skipping for this maze. But if you want, you can do it on your own. All right. So how will we do? You see, at start node S, we are branching. We have two ways to go. And you can think about it as there are two children. And I told you, for a child at this node, you can take anyone randomly. You can take, you can put it in the stack in any order. So over here, the algorithm randomly takes right. So from S, it goes to right. All right. So it could have taken down also. It depends upon what your algorithm is doing. If it is random, it can take any path. So it goes here. Now, just think about the tree. So it is going. So this is just the tree. Again, the action it can take is down. So over here again, there are two child. Randomly, suppose it is again going right. All right. So randomly it is again going right. So when it has come right over here, it has only one action it can take, which is down. So it goes down. When it goes down, it sees that there is no other path. So there is no children. So it will backtrack. So think about it like this. So it started over here. It started at A. It went to M. It started at A, went to M, and it saw that there is no child there. So it has to backtrack, come back. And over here, it came back to K and went to L. So that is what it will do. So over here, it went and it saw that there is no child over here. it went back and it came over here. It will go down and come over here because there is no other action. Over here, it has a choice. It can either go left or it can go down. Suppose randomly it has gone down. So it will come over here. Again, it has a choice whether to go left or right. So suppose randomly it goes right. And yeah, so it goes right, it goes here, and it has found a solution. Now what you have to do, you have checked that this is a solution. You can, so that is why I was telling you with the state you have to keep its path it has taken. So when you have reached G, you have to track back what the path it has taken. So that is how you will get the path, right? So over here, if you see that this algorithm has given me a solution, and this is not the best solution it has. You see that this is the path which will take less amount of steps, right? But since depth first search assumes that all the path costs are 0, it will stop whenever it has got a solution, and therefore we have got a solution which is not the optimal solution. It will just stop, right? So this is how depth first search works for this maze. Any questions?
None questions.
Okay. So we will go to breadth first search. Before that, it's 7. We will take a 5 minutes break and we'll come back at 7:06. All right.
Okay.
So any questions do you want to ask? All right. So we'll wait for 2 minutes and then we'll start.
Hi Shubham.
Yes.
Shubham, could you please share the slides, Shubham? Those
Yes, I have
slides.
shared the slides. It's there in my website.
Oh, okay. Thank you, Shubham. I will see.
again, if you realize in this maze solving problem, you see we are constructing a solution. We are taking a step and we are saying this might be the way to reach the solution. So this is a construction heuristic, constructive heuristic. Yes. Um, so do keep in mind we are constructing a solution. So when we are reaching the solution, we have to track back and get the whole solution. So these are construction heuristic. I'll get the term from the book and tell you. Constructive heuristic. It's constructive heuristic.
What do you mean by heuristic over here?
Yes, so heuristic is actually in English it is known as it means shortcut. But in OR it's algorithms which gives approximate solution. Actually in OR it means that it will give you a solution, but you will not be able to tell me how good it is. It will give you a reasonably good solution. That is what a heuristic means in OR field.
So does it mean that it is giving a solution, but we don't know whether it is a minima or a maxima?
No. So suppose if you have a minimization problem, a heuristic will give you a solution that will be reasonably good. You don't know if it is the optimal solution or not, but you know that it is the best it could have it found.
Okay.
All right. So breadth first search. So what breadth first search does is it explores level by level. So what it will do is it will go to level S, it will explore, then it will go to level 1. Sorry, it will go to level 0 where it will explore S, then it will go to level 1. It will explore A and B. Then it will go to level 3. It will, not level 3, level 2. It will explore C, D, E and F and so on. So this is how it will go. It will explore the levels and then go to the next level. This is how breadth first search works. Now you will ask me, how is this useful? You see, this is useful when the path cost is constant. So suppose the path cost is C for all the actions. So all the path costs are C. In such case, if you explore level by level and suppose C is the solution, when you reach C and you know it is the solution, you don't have to go down. You see, as you go down, the tree explodes, enlarges. At every level it is branching, at every level it is branching. So the further you move down, the more you have to search. So breadth first search helps you reach a solution if you have a solution at a higher level fast, right? This branching will take you a lot. So if you have a lot of branches and if you do depth first search, it will go one branch at a time. And depth first search says that if you have a solution at any, so suppose you have a solution at this node C, what is the cost it is taking? It is taking C plus C, 2C, right? And if you have any other solution, suppose M is the solution, what will be it cost? C plus C plus C plus C, it will be 4C. So the better solutions will be at the top if all the path costs are same, and that is how breadth first search benefits. All right.
Yeah.
Any doubt?
Yes.
Okay. So you see the action costs are constant. What is the space? So you see over here we are gaining in time. We'll let you know what is the time, but we are losing in space. You see, you have to keep track of all the paths you have taken. Otherwise, when you reach a solution, you will not be able to backtrack. So over here, whenever you are at a branch, at a level, you have to keep store all the branchings above. So at each level, so over here you have to keep 2 branch. So B. At this level you have to keep B. At this level you have to keep B. So B to the power D. That is the space complexity. Order B to the power D. Over this D, why this is not, I am not writing capital D, because you may encounter a solution at a higher level. D is the depth of the tree, capital D is the depth of the tree, and this D can be less than capital D. That is why I'm not using capital D, but small d. Right?
Yes.
This time, over here, time is also decreasing. You see, earlier the time was order B to the power capital D. Now it has become B to the power small d. So in time also you are gaining. In the worst case, it may happen that D is actually equal to D. In such case, it is same. But Generally, it is seen that, so I'll not say generally, if you have the solutions at a higher level, then you will gain in time. You will solve the problem at a faster rate, right? So this is the time complexity and space complexity. So we'll solve the maze problem again using breadth first search. So remember, okay, this will be white. I have by mistake labeled, make this as gray. So this is actually not a wall, all right? Okay, so how is this breadth first search works? It will be at a level, explore the children. Again, at that level, it will explore its children and so on. By the way, this breadth first search uses Q. I will show you Q, UE, UE. So how this Q works, it is actually first in, first out. So I'll show you over here, Q. So think about it as a list. You put it, so whenever you are putting data, put it from the back side, but whenever you are extracting it from it, you take it from the front. So that is how first in, first out. Whichever has come first will come out first. So over here, you are at level S, level 0, you are putting S in the queue. So we are saying S is in the queue. Now you are dequeuing it. So S is coming out. So I'll just cut it. What is its children? A and B, put it in any order. So suppose A and B. Now you have put A and B. There are no other children to put. You then take out A and explore its children. What is the children? C and D. So put it in the queue, C and D. Now next you have to explore B. So put out B, take out B and put its children, E and F. You see, we have explored this level, we have explored this level. Now you take out C, it doesn't have any child, so you nothing to put it inside the queue. When you come to D, it has two children, G and H, put it in the queue. So you see, it is like putting it from the back and take it from the front. So this is how queue works. So whenever you are implementing this in Python, take a list. Whenever you are adding, add it at the last, and whenever you are extracting, extract from the front. So that is how you will be able to do breadth first search. You don't need to keep track of the tree in an imaginary way. I have to go by level. How will I go by level? Should I keep a marker at each node that this is level 1, level 2? No, you don't have to do all of this. If you maintain a queue, then automatically the levels will be taken care of. You don't need to track the level also. A queue helps you do the breadth first search. Is that all right?
Yes, sir.
Yes.
Shubham.
Yes.
Shubham. Can I make a breadth first search algorithm to use a stack approach?
So what is a stack? Stack is actually last in, first out, right?
Last thing. It's the reason behind asking this question is breadth first search approach is a transverse to the depth first search approach. Means if I in a matrix language, if I transverse the breadth approach, it becomes depth approach. Just 1 by 5 transpose is 5 by 1.
Sorry, 1 by?
First row, fifth element, first row, fifth column. If I transverse it, it becomes fifth row, first column.
Yes.
So in a similar means breadth, shall I see breadth first search approach as the transverse of depth first search approach?
I'll not be able to answer that question right now because I don't have an answer to that question. I'll check and let you.
Please. And one more thing, just please let us know that whether LIFO approach, stack approach can be used for breadth first search.
That you will not be able to do. You see, when you are doing, okay, if you are doing transpose, yeah, I'll check and let you know.
Okay.
I will have to see what is a transpose of a tree. I don't know. Yeah, I'll check.
But
Okay,
in this
so,
case, in
yes.
this breakfast case, then while we shall be saving the nodes, along with that, the node level we have to save. Correct? Means S means 0. A we have to save in that queue. Along with that, we have to save 1.
No, sir.
Then B.
Not able. No, you shouldn't. Yes,
But
sir.
whenever we'll be at a position of E, we may not be able to recall at which level we are.
You don't need that. You have to store its parent. So suppose this is the solution. Suppose S A and C is the solution. You just have to store its parent. So what is the parent of C? A. So suppose for example M is the solution, right? So I'll just erase and give you one better example.
Then here we are just searching, not optimizing. Is it optimizing?
We are optimizing, right?
Okay, yes, we are if we are optimizing, then we have to say we have only not got it, but at the same time at which level, means what is the path cost that we are not expecting.
So what are we doing is, for the cost we are adding it up. So whenever we go at one more level, we will just add the cost plus C. So when the next
okay. So whenever the B will be exhausted, whenever it will start from C, we shall add the cost.
So that will help you at last. So when you have obtained the solution, suppose you have obtained the, so suppose M you have obtained, M is the solution. When you backtrack, you can see how many parents it has, and you know the path cost for the path. So at last you can do it. You don't need to keep track of the levels when you're doing the breadth first search. You can obtain the cost once you have a solution.
Okay.
So you don't need to keep track of the levels in a queue. You just have to maintain that order. That's all. That is how this data structure works. It helps you do this breadth first search. All right, so we'll see breadth first search over here. So at any node, it will just branch and explore both its children. So what it is doing is, from S, it is exploring these two. Again, it is exploring these two. Again, it is exploring these three. Now, one thing you should note is, when I am saying level 4, you see, it is actually at level 4. So wherever it is actually at level 4. So it is 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, right? So it is at the same level 4, right? So over here, what it will do, it will, so you see over here, it can go over here, or it can go over here. It has only one way to go. It can go over here, and it has only one way to go over here. And I have just labeled it as step by step. You can see at your leisure time. So this comes over here, this comes over here, this comes over here. This will come at a dead end. It will come over here and see it merges. Now it comes over here and then explores both the sides and then go back and get to G, right? So this is how breadth first search works. Now once you have reached G, you have to backtrack. So whenever you are proceeding, you should keep one more data, that what is its parent. That data you should keep. That is how you will be able to backtrack, and then you will be able to get the cost. You see, breadth first search has actually obtained the path which is at the least cost. This is the least cost path. The depth first search obtained this path, which was not the least cost, right? It could have obtained, but in my example, it did not obtain. All right. So I have mentioned all the three algorithms over here. Now, one thing I would like to mention is, these are very small increments in time and space. So it is very small improvements. There is one algorithm known as dynamic programming. I'm not going into that because I have not kept it in the syllabus. But this algorithm is polynomial time. It runs in polynomial time and it can solve the problem. It has an assumption. It says that the path cost, the action cost cannot be negative. So it has to be greater than equals to 0. The first assumption for dynamic programming. And the second assumption is there shouldn't be any cycle. So no cycle. There shouldn't be any cycle. If these two cases are met, then dynamic programming is very fast. And if you have taken some programming course, dynamic programming is just recursion plus memoization. So if you know what is recursion, it calls itself over and over again a function and keeping memory. So these two together is actually dynamic programming. And if you want, I can take this in some other time, maybe on Tuesdays. All right. So dynamic programming is a good algorithm which can solve problems having these two properties. Action cost is greater than equals to 0 and no cycle. In such case, you can solve the problem very fast. All right. Okay. So this example I have kept. You can. I'll solve this problem. All right. So we have S, then A, B, C, D, and E. So I have shown you how to keep track in. Yes.
I have a question. Is there any difference between the capital D and small d? Or both of them mean depth only?
No. I'm saying capital D is actually the solution depth. So the depth at which you're finding the solution. Capital D is the maximum depth of the tree. All right. Okay. So this example is actually showing you a stack and a queue. So why I have done this, because if you have to code this, you should be able to understand how to code this. And I have given one pseudo code also. I'll show you. So you see, you are starting at a stack with one element, which is S, and you are keeping track of visited. Why are you doing this? Because it helps you to, read. It helps you keep the memory. And one more thing, it helps you. You shouldn't, if you encounter that node again, you shouldn't explore that again. So you will understand when you solve a problem. So you see, you are starting with S and you have not visited any node yet. So what you will do, you will pop S and you will say that you have visited S. So you will put S in visited. Now when you have put S in visited, you will put their children in the stack. So what are its children? A and B. So now the stack becomes A and B, right? So this is the new stack. Again, you have to, so what we are doing? We are doing depth first search. So it is last in, first out. So what is the last? B is the last. So B will come out. You will say you have visited B, and then you will put its child. So over here, B's child is E. So you will put E in the stack. So we are saying the new stack is A and E. So this is how this depth first search work. You can go through. It is the same which we had discussed earlier. This is breadth first search over here. And one thing you have to, so what I'm saying is, one thing you have to be sure that in stack, we keep one element in visited whenever we pop. So when we pop, then only we keep that element in visited. In queue, we keep that element in visited when we are enqueuing it, when we are entering it in the queue. So this is one difference in stack and queue. So again, I'll tell you, in stack, whenever we pop, whenever we take it out, then only we keep it as visited. We have visited it. In queue, whenever we are putting it in the queue, we are enqueuing it. It is known as enqueuing. When we are putting it in the queue, we label it as visited. We have visited S. So I'll give you later maybe some examples of why this is important, but you should keep this in mind. All right. So you see, we have S in the queue and we are saying that S is visited. Now we DQS and we say, what is its children? We'll put A and B in the queue, and then we'll take out A and B, A. And when we are putting it A and B in the queue, we are saying A and B is already visited. All right. So I'll just, this small thing you have to make sure. Now I have given you pseudo code of depth first search and breadth first search. All right. So why I have given you this, I will give you an assignment of writing the same algorithm in Python. So over here, what I have written is very similar to Pythonic language. Few things I have not written. So this is the algorithm to solve the problem, but I have not written how to model that problem. So modeling you have to write, and solution algorithm I have given here. So those who don't know Python, I'll take one class on this Tuesday. We will discuss basics of Python, and then you will be able to submit the assignment. I don't think this basic Python will help you a lot. You have to learn Python from your end also. All right. So this def means we are declaring a function. So the function name is DFS, and we are keeping a stack, and I'm saying S is at the stack already. I'm keeping a set visited, and I told you we have to keep this parent. So whenever we are visiting a node, we should keep track of its parent. So I have a dictionary. So we have a data structure in data type in Python known as dictionary. So this is an object in Python, and I'm running a while loop. So what it is doing, it is checking if the stack is empty or not. Now I am popping the stack. So in Python, pop means from the end. So I'm just writing pop in queue and stack. In both of them, I'm writing pop. But you should remember when I'm saying queue, so it is actually dequeuing it. So you have to pop from the front. So in depth first search, I'm taking one element. I am checking if the state is the goal state or not. So you have to see if that state you have popped from the stack is the goal state or not. If it is goal state, then we will see what this is. You have to return the solution and the path you have taken. So this function reconstruct path help you trace back your steps to get the path you have taken to come over in the goal state. And also the cost, it will tell you what is the cost. So it checks if the current, so what is current? Current is when you pop, I am storing it in current. I'm checking that state is the goal state or not. If it is goal state, give me the solution. So this return will give you the solution. Now, when I have popped in depth first search, whenever I pop, I have to store it in the visited. So I have stored it in visited. Now what I do from that element which I have popped, I have to see what are its children. So this for loop will give me its children. So for example, over here, I was in S. I saw its children are A and B. So this for loop will actually give me A and B. Now what it will do, it will check if this A, is it visited or B, is it visited? It will store its parent. So for A, it will store S. For B also it will store S, because I told you at each state you have to keep track of its parent. So this is storing of parent. And what is this is you are appending it to the stack. So when you have got A and B, you have to add it back to the stack. So append is a function in Python which helps you add back to the stack. All right. So this is how, and this loop will run until and unless the stack is empty. So we have a while loop. And if this while loop terminates without coming over here, so if you have not reached the goal state, then it will return no path found. All right. If you have not understood this, please go back and learn basics of Python, and then we can discuss this again. All right. So this is very simple. Now you see few functions I have not written. So this reconstruct path function I have given you. How to get a neighbor I have not written. So this function I have not written. How will you get a neighbor? So these you have to think. So these are modeling aspect. How will you store a tree? So I have given you are entering a maze over here, right? So these things you have to think about. I will discuss the solution of this problem in the next class. Before that, you should think about how should I construct the tree? How should I keep the tree? So for example, for a maze, you can keep it in as 0, 1. So you can have a n cross n matrix, and 1 represents a wall and 0 represents empty space. So this is how you can store a matrix, maze. And how will you get a child? So you see, we were talking about state space search and the elements. So there was a function which takes an action and a state and give you the next state it can go. So that is how you can create a child. So suppose you are at the current state. So I'll just erase everything. So suppose you are at the current state. So over here you are entering the current in this function. So you are saying this is current and you are giving the maze to this function. So what this function will do, so suppose this is the current state and this is the maze. So this function get neighbor, first it will see what is the action it can take from this state. So it can go up, down, it will check, and then it will give you what is the next state it can go. So over here it can go right, it can go up, everything it will give you back. So this neighbor will be that, and you have to then store that neighbor in the stack. Now what will be the structure of this neighbor? It is same as state. So neighbor is what? It is a state, right? Are you able to understand this or not?
Yes, getting it.
Any doubt? So suppose you have started with 0, 0. So this was the start state. Now what this get neighbor will do is it will take this maze, it will take this start state, it will give you 1, 1, and suppose so from here you can not go to 1, 1, you can go to 1, 0 and 0, 1. So these are the two neighbors you will get from that function get neighbor, and then you will add it back in the stack and so on. So that is why we were doing the modeling. All right. So if you have question, please ask me, because this is very important. Are you able to implement that?
For neighbors, in case we have two places where we can go to, like if you have two branches, how is it going to select which branch is it going to go?
So that selection will be done later. First, this function for loop will give one at a time, and that will be added to stack. And that stack is actually taking care of depth first search. So we have seen, right, how stack was working. It is adding back to the stack and taking it back. And this function, this if statement, if the goal is equals to the current or not, that will help you that will tell you that you have reached the goal or not, right?
Okay.
So for example, in this node, suppose C is the solution. So what this will do is it will go deep and it will see if A is the solution or not. It will say no, it is not the solution. It will go to C, it will see yes, it is the solution, and it will terminate, right? It will terminate there. And because we are doing depth first search, there is nothing like what is the cost of the path, because we are saying in depth first search, path cost is 0. Is that all right?
Yes.
If you have doubt, please ask me, because it may become more and more engaged, right? More and more engaged. Yeah, that is a good term. So breadth first search, this is same as depth first search. You just have to replace stack with a queue and nothing like that sort, but just you have to see how are you taking it out from the data structure you are storing. Just you have to do first in, first out, and last in, first out. That is it. You have to check. And one more change over here, we are storing the visited when we are popping, but over here I am storing whenever I am enqueuing, whenever I am putting it in the queue, right? So this is the two changes. Everything else remains the same. This is the function which gives you the solution. So when you have reached the goal state, it will take, so what it will take the parent, start, and goal, right? Just a minute, I have written parent. Okay, it will take this. It will take the set of all, so all nodes and its parent. So it is actually a dictionary. It will take that dictionary. It will take the start state and it will take the goal state. What it will do is it will try to construct the path. So it will go back. So it is at, so suppose over here, I'll just come back over here again. So suppose it is at E, it knows what is its parent. So it knows it will be B. So from E, it will construct B. From B, it will construct S. So it has got this path. Now it will just reverse it. It will say S, B, and E is the solution. That's it, right? So this function is doing that, just that. All right. So it is taking the goal. It is, you just go through it. It is just doing the same thing which I have explained right now. All right. Now we'll do A star search. Any questions?
No, sir.
Okay. Now what is A star search? You see, when we were doing this maze problem, we were exploring its children as if, because we had no knowledge where the solution is. So we were just exploring everything, as some intelligence was there, but we were exploring everything. This algorithm is known as informed search. Why? Because it uses something known as a heuristic, and this heuristic is actually estimating the future cost. So suppose in a maze, so suppose for this maze, I'll just go back to a maze. So suppose this is the maze and I am at here. So I'll just take, yeah. So suppose I am here. So what it will do is this heuristic, it will try to estimate what is the future cost. So from here to here, so reaching from here to here, what will be a cost, approximate cost, right? So from here also, so you see we are at 3 levels, either we are here or here or here. We can take a judgment. So suppose I have estimated some cost from going from A to G. So I'll just label this so A, B, and C. So suppose I have obtained a estimated future cost that going from A to G takes me 10 units, going from B to G takes me 6 units, and going from C to G takes me 3 units, 3 unit of cost. So what this algorithm is trying to do is estimating some future cost. From A to G, I may take 10 units of cost. From B to G, I may take 6 units of cost. And from C to G, I may take 3 units of cost. Then it will take, that's going from C is better, then it will explore that region of the maze. It will not explore A and B further. All right. So this is how it is estimating future cost. All right. So you see, in a maze problem, this heuristic, in a maze problem, this heuristic is actually the Manhattan distance. So what is a Manhattan distance? What it does, it removes all the walls. So suppose the walls are not there. So from here, what is the cost to reach G? You see, it will take 1, 2, and 3 steps to reach G. So it is some estimate to reach G, right? Again, from here, what is the cost to reach G? Suppose the walls are not there. So this is 1, 2, and 3. So I have labeled this maze with that heuristic. It is just estimating the cost to reach G. It might not be always correct, but it is trying to estimate some cost, right? So from here, what is the cost Manhattan distance? It is saying that, see, I am here, 1, 2, 3, 4, 5, 6. So 6 is the cost of that cell. All right. So this is the future cost. Is that correct? Is that all right?
Yes.
Sir.
Now we will do informed. So this is the information I have, and now we will do the search. That is why it is known as informed search. So you see, when I am at S, I have two options, whether to go to a cost 6 or to go to a cost 6. I can go anywhere, right? Because both of the costs are 6. So I have taken this path. I could have taken any other path, but because both are costing 6, I went there. Now, when I am here, I have a decision to make whether to go to a cell with a cost of 5 or to go to a cell with a cost of 6. Now I will think if 5 seems better, I should go that way. So we have moved over here. Again, when I am here, I will think whether to go to a cost of 4 or to go to a cost of 6. So I'll go to the cost of 4. And this is how that this search will proceed, and I'll reach 2. Now when I have reached 2, I'll see there is no way further. I backtrack. When I backtrack, I see I have a cost of 6 and a cost of 4. What will I take? I'll take the cost of 4. So I'll go over here. Again, I will see I can go to a cost of 3 or to go to a cost of 6. So I'll proceed this way. When I am here, again I have a decision to make whether to go to a cost of 5 or to go to a cost of 6. Sorry, not 6, 3. So it will proceed like this. When over here, you see, it can go this way or this way, but it knows that going to the right will be at a cost of 3. Therefore, for sure, it will go this direction. In the breadth first search, it went both way. In depth first search, it could have gone to left also because it was choosing randomly, either this way or that way. But over here, we are clever and we are going right and not left. So it will go this side, and then reach G. All right. And then we can just backtrack and get the solution. Is it all right?
Yes.
So I'll show you one video, and then that video is from the internet, and you can see how good is A-star algorithm. In that channel, there is one more video of uniform cost search. We are not discussing that here, but that actually searched a lot of area, but this, I'll show you the video. Okay, I'm not able to click it here. Sorry. Achha, but there's a video over here. You can just go and click there and then you will be taken. Achha, I can do that, right? Just give me a minute. I can do that. I have not embedded it or what? Okay, I'll just embed that video and okay, yeah. I'll just mute the video because the sound is not important. So what is it doing is it is starting from this green point, the lower green point, and it wants to reach the topmost right green point, and it is doing A-star search. So it is always trying to go using the Manhattan distance right ways. All right. And think about it. If we are doing breadth first search, it would have explored everything and then went above, right? Yeah, so you get it. So this is how A star search works. All right, I'll just exit this now. You can just watch it afterwards. Okay, so advantage, it finds the optimal solution when the heuristic is consistent. So you see, we have talked about one heuristic, which is the Manhattan distance. There can be multiple heuristics. The more accurate your heuristic is, the better your algorithm will be to solve that problem. Now, what is consistency? Whenever I talk about consistency, there are two properties the heuristic should meet. It says that the cost. So you see, at each state, it is giving you a cost. So suppose I am representing that cost as C dash, right? So over here, I am saying the cost C dash is 4. Over here, I am saying the cost C dash is 3. So the cost at the end state must be 0, right? So that's obviously at the end state, the cost is 0. So if that heuristic is giving that, that one condition is met for consistency. The second condition is if you are at state S and if you go to state S dash, so there is a cost engaged from going S to S dash. Now what are you doing? So I'm representing that cost from S to S dash as S comma A. So this is how I am representing. So I am at state S, I am taking action A, and it gives me the cost C S S dash. So that is the cost of action A staying at state S. That means I am at state S. When I go to S dash, I incur a cost of CSS dash. Over here, for example, I am over here. I take one action, that is move left. It has a cost of 1, right? So if this represents the cost of taking one action, one step, and H of S is the heuristic value at S, what it means? Over here, H of S is 4, over here H of S is 3, over here H of S is 2, and so on and so forth, right? So it says that actually it is trying to have the triangle inequality. It says that taking the cost from S to S dash plus heuristic cost of S dash should be greater than equals to H of S. So think about it as a triangle. So suppose you are as S, this is S dash, and this is end. This is the cost of going from S to S dash, C S S dash. This is the cost H S dash, and this is the cost H S. It just says this plus this should be greater than this, greater than equals to this. I don't think equal to is there. I have to check. No, equal to will be there. Yeah, greater than equals to this. It is the triangle inequality. So the sum of two edges must be greater than the third edge. If these two conditions are met, then you have an optimal path. Very important, right? So the solution you will obtain from this algorithm A star will be optimal. It is very important, right? Optimality is very important. You are obtaining the optimal solution. There is no other solution which is better than this solution. It can handle large search space efficiently. Disadvantage, it is more memory intensive. Again, you have to take care of heuristic solutions at each state. Performance depends upon the heuristic. If your heuristic is good heuristic, then your performance is good. If your heuristic is a bad heuristic, then your performance is bad. It explores unnecessary node. So if your heuristic is not well designed, obviously it will wander here and there, right? So this is the advantage and disadvantage. So this completes state space search. Any questions? Okay, so we will go to adversarial search. We will not be able to complete this because I just have 15 minutes, but I'll give you some idea. Okay, so what is adversarial search? It is just a game where we have players and they are competing with one another. All right. So, and one more thing, we are talking about zero sum game. So I'll let you know what a zero sum game is. So zero sum game means if I win $10, then you lose $10. One wins, other lose. That is how a zero sum game is. ऐसा नहीं है कि दोनों ही जीत सकते हैं. So that is what a zero sum. So for a chess, if I win, you have to lose. That is what a zero sum game is. And one more thing. So this is one thing, zero sum game. The second thing is it is a sequential game. So for example, a chess, I will play a move, then only you will play a move, and then I will play a move, and then only you will play a move. On the other hand, if you think about rock, paper, scissors, so we are playing simultaneously. My action and your action will be played simultaneously, right? Rock, paper, scissors is not a sequential move game. It's not like that I will play something, then you will play something. So over here, we are talking about sequential game. I will make a move. For example, tic-tac-toe. I will make a cross, then only you will make a circle. It's sequential, right? So sequential game and a zero-sum game. So tic-tac-toe, all right? So there is one algorithm which is known as Minimax algorithm, Minimax, all right? So this helps you obtain a solution to this problem. What is the problem? It is a game which is a sequential game and it is a zero-sum game. Now we can represent this as a tree. All right, so for example, take a simple game, and this example I have taken from Stanford lecture. All right, so suppose there is 3 bags, 1 bag, 2 bag, and 3 bag. I will draw it a little bit down. Maybe there are 3 bags, 1, 2, and 3, and it has coupons. So this has a coupon of -15 and 15. 2 coupons are there. It has a coupon of 1 and 3, and it has a coupon of maybe -5 and 15. All right. Okay, so these are the 3 bags I have, and what I'm saying is you choose a bag. I will tell you what coupon you have to. So you will choose a bag. I will choose the coupon. So what it is doing is you are playing first. So you are playing first. Either you are choosing this bag, so bag A, bag B, bag C, and I am choosing the coupon. So I can choose either -15 or 15. I can choose 1 or 3, or I can choose -5 or 15. All right. So this is how. So you are moving over here. So this is your player 1. So I'll just say player 1, and this is for player 2, where player 2 moves. All right. Now tell me which bag you will choose. Which bag you will choose?
Player 2.
No, not
B.
player B.
B.
Why? You are not trusting me, right? I could have given you better options, because you see there are better options, right? So suppose this is 1 -150 and 150. So there are better options. You could have got 150. So this is because you are uncertain about my intentions. I can be a player who is trying to sabotage you. So this game, adversarial search, thinks about in that direction. It takes the assumption that the other player of the game is trying to sabotage you, right? That is why it is a zero-sum game. If I will win, you will lose. So if you choose bag A, I will intentionally play -150. You will get -150, right? So it is that way. Is it okay? Right. So yeah, so you can have 3 cases. -1 and +1 you can represent. So -1 is you are losing and +1 is you are winning. And now you see about this, why we are calling it why are we calling it Minimax? You see what this player is trying to do. This player is trying to maximize the value. And what this player is trying to do, this player is trying to minimize the value, right? So that is why this algorithm is known as Minimax. And what will we do is we will backtrack. Now think about, you are at this node. What is the best option? Player 2, because player 2 will move in this node, right? In this node, player 2 will move. What is the best action for player 2? Player 2's best action is to play -150, because he's trying to sabotage you, right? Please tell me you are understanding the idea. Right. Okay. Now if you are at this node, what will player 2 do? Player 2 will try to minimize the value you are getting. So player 2 will choose this option. And when you are at this node, what player 2 will do, player 2 will choose this action, right? It is sorry, this action. Now what player 1 will do is he will just forget about this and he will say that over here I am getting minus 150, over here I am getting 1, and over here I am getting minus 5. What is the best option for me? To go for 1. Therefore he will choose B. So this is the Minimax algorithm. That is it. That is the simple idea of Minimax. We will backtrack from the leaf nodes and we will reason it out till the front. And remember, this is a sequential game. So at a node, only one player plays. So at this node, player 2 will play, not any other player will play, right? So both the players are not playing simultaneously. So this idea comes from another field in economics, which is known as game theory. This is also a very important field where I will give you some examples, but yeah, it helps in understanding markets. So suppose there are two competitors. What should I play such that I get the most customers? Because the other player is trying to get the market share, I am also trying to get the market share. So something like that. This is one application of game theory. All right. This game theory has developed from economics. It is used in operations research also. All right. So this is what min-max is. And we will talk about alpha beta pruning. We will see what it means in a later time point. Just, yeah, so we have talked about this. So let us take an example of tic-tac-toe. So how will you code a AI agent to play a tic-tac-toe, right? So you can code this in your computer. If you are well versed with this programming, then you can easily code this game. It is a very simple game to code because you can think about it as a state space search. You have a state, but over there in state space search, you don't need to think which player is playing. Over here, one more thing is added, that at a node, you have to decide which player is playing, and whichever player is playing, then their action will be decided upon which player is playing. And that is it. It is similar to state space search. The only difference is at each node, you have to think which player has to play, right? So at this node, we are starting. So you can start actually above this also. So suppose there is the empty tic-tac-toe grid. So I have actually not started with the starting, empty starting, and suppose there were multiple options from here, right? There can be multiple options. X could be here or here or here or here or here. It could have been any place, right? But I'm saying, suppose we were at this node. Now there can be not two child. I have drawn, because of space limitation, only two child. There can be actually 8 childs. O can be here, or it can be here, or it can be here, and so on. So there are 8 children to this node, right? Am I making sense?
Yes, yes, you are.
Yes.
And at each level, one player is playing, right? So at this level, player X is playing, at this level, player 0 is playing. Now, how to reason this out? You see, suppose you are at this level. So suppose you are at this level. What will be the AI agent do? It will construct the whole tree. It will construct the whole tree and it will see which child, which child will give him or her lead to, which child will lead to him or her winning. So suppose this child will lead to him getting +1. So suppose player over here, player is the agent I, and if he wins, he will get +1. And suppose I am playing against him, so Shubham, so agent I is playing X and Shubham is playing O, right? And if I win, I will get -1. Now, agent I is thinking, where should I place this
So
cross?
from the very first go, how it is going to decide who is going to win?
Actually, it will explore the whole tree. And because in the first action, it doesn't matter where it play, because any action will lead him to win, so he can randomly choose where he can play. So suppose we are not here, suppose we are at this node. So I have taken one example. Suppose we are at this node. What will the AI agent do? Because it is O's turn, so suppose O is the AI agent for now. So O will place one children like this. Again, it will place one child over here. It will place one child over here, and it will place one child over here. And then again it will branch. So for these 1, 2, 3, 4, for each of this child, what can X player do? Those many branches. And again, for each of those nodes, what could I do? And it will explore the whole tree and then see which is the best one, either this one or this one or this one or this one. Right? So you see, when AI agent plays 1, he will know that he will lose because he has explored the whole tree and he will know that player X will play X and he will win. I will get -1. So he will not play 1. Again, for 4 also, he will see if he plays 4, he has explored the whole tree and he knows if he plays this, then the other player will play X and he will win. And for this also, he will see that if I play 2, the other player will play X over here and he will win. Therefore, the best option to take from this state is to go in this. Therefore, the AI agent will play 0 over here, O over here. And this will be the best option for him at this node.
So do we need to provide a cost for each child?
No. You see, in these type of games, the utility is only obtained at the end when you have the game is terminated. So the AI agent will explore the whole tree going down.
Okay.
So if it is not clear, I'll give you one example. So I have taken such example also. Okay, before that, I'll show you one more example. Before that, how will we model? We have states. Sorry, I have not written. There is a states also. So states, what will be the states? Initial state, player. So you have to decide at this state what is the player, what is the action, what is the result, that is the transition model, whether it is the goal state or not. So termination check, and what is the, so I'm writing utility over here. It is actually the path cost. So I have taken one example, just let me go there. Yeah, so suppose this is the example. So this is not talking about min-max, but I am taking this example because I want to discuss something. So suppose in this game, these are the numbers, and suppose it is actually here 9 and over here it is 5 and 6. Okay, so these are the numbers I have. Now forget about this right now. So what the AI agent will do, he knows that this is the termination of the game. Okay, this is the terminal node or the leaf node. So he had explored the whole tree. Suppose this is the tree he is coming from somewhere else, and over here he will see that these are the utilities he is getting, and here is the min player. So what will the min player do? The min player over here will try to minimize the value. So the minimum value is 14. The minimum value over here is 9. And the minimum value over here is 6. Over here, the agent will think over here I am getting 14, this I am getting 9.
Last value should be 5.
Okay, yeah, sorry, 5. And this agent is maximizing. So this agent will think I'm getting 14, I'm getting 9 and getting 5. So I should play this. Now, how about tic-tac-toe? So take this example of tic-tac-toe. All right. So to take the example of tic-tac-toe. In tic-tac-toe, suppose this is the tree. Obviously, this might not be the tree. So suppose I am assuming that this is a tree of some game where there is either win, lose, or tie. So suppose this is lose, this is win, this is win, this is lose, this is tie, this is tie, this is win, this is tie, this is tie. I have min player over here. All right. I have min player over here. So think about, suppose this is chess, and these are the terminal nodes, and these are not the utilities. I have written the utilities in red. So over here it is -1 1 1. This is -1 0 0, and this is 1 0 0. 0 means tie. -1 means the max player loses. So the max player loses at max player lose, and +1 is win for max player, right? So what will the min player do? The min player will always choose the minimum value. So over here he will choose this action because he will get -1. The min player over here will choose this value because not he will get, because the max player will get -1. And over here the min player can either choose this or this, so it will get 0. Now he knows, this max player knows that if I choose this I will get -1. If I choose this, I will get -1. If I choose this, I will get 0. So the max player will choose this action because in this action he will get 0. Think about in tic-tac-toe also, no? So when you play with someone, you think, right? So when I place this, what will the other player do? And what should I do next? So that is how the reasoning is going over here also. Is it clear?
Yes.
Anyone has any other question? Okay, so this is about min-max. And since I don't have any more time left, I will talk about alpha beta pruning in Tuesday. So what is the plan for this coming Tuesday? I will talk about, first I will finish this part, alpha beta pruning, because some might not be interested in Python. So basics of Python. So I'll finish this part first, alpha beta pruning and whatever I wanted to finish today. And then we'll proceed with whatever I have to discuss in Python. And then maybe I can discuss the algorithms again, the depth first search and breadth first search again. All right. So just let me see whatever I have left, how much it is. Yeah, and this is also left. So before completing, before concluding today, so we have seen an algorithm Minimax, it explores the whole tree, right? So you may think kitna bekar algorithm hai, it has to explore the whole tree. So there are two more ideas or two more improvements to this Minimax. One is alpha beta pruning and the second is limited depth Minimax. These two you can say improvements can help this algorithm run faster, because if you think about chess, there are billions and billions of branches in that tree, right? So there has to be some other algorithm which will not make you explore the whole tree. So these are some of those ideas: depth limited minimax and alpha beta pruning. We will talk about this in this Tuesday. We will meet at 6 p.m. as usual, right? And yeah, these are the references I have used. So these are some of the lectures by Stanford and Harvard and other NPTEL lectures. Okay, so any questions? Yeah, Saurav had some question. You can wait. And if anybody else has some doubt, you can also ask me. And if you have any suggestions such that I can improve my teaching, you can also give now. Okay, so you can leave. I'll get the attendance sheet. I'll just share it with you. I have not made the assignment yet, so I will upload it maybe tomorrow. So I have not yet completed the assignment, and the deadline will be before the next class. Next class, I mean next Sunday. Okay. Thank you.
All right. Thank you.
Thank you.
Yes, so anybody has any questions to ask? Is Saurav here? I don't think he's here. Okay. All right, so yeah, then I'll end the meeting now. Thank you for joining.